We have strong rules in this university now about where you can and cannot post locations of things. This is why your slide deck does not have the location, and my slide deck does have the location. And I will be posting location to Piazza. There is a midterm coming up. If you did not know this, it's a good time to take note of this fact. I submitted the midterm for printing at about 11 o'clock last night, so it is now finalized. The university has this awesome threat called submit it on time or you have to print it yourself. Go down. It has 24 questions. 2 of them are fill in the blank, but it's not a singular blank, it's several blanks. 14 are multiple choice or multiple select, and 8 are open-ended. Historically, this midterm has been a multiple choice question sort of thing in the past, and so this is why you're seeing a bit more leaning towards multiple choice. I am expecting the final to look a lot more like the finals on the website. So this is leaning kind of towards the final, but the final will have probably less multiple choice numbers. And 8 are open answer. That means I ask a question and I say something like, tell me why the above is true, and make sure you justify your decisions. All the modules we have covered up until this moment are directly examined. The networking module, I have not put anything direct on there about networking because we're kind of behind on that, but I am using some networking terms in the other questions. Man-in-the-middle attacks, as a rough example, often happen over the network. So as a side effect, I am expecting you to have a reasonable understanding of what I would consider to be common in networking terms, like IP address, connection, things like this. So you will see words like that in other questions, but I'm not directly examining the networking content. All right, you guys have me worried. There are about 60 of you that I think maybe are going to be in trouble. The first year I taught this class, I failed about 20% of it. Shocked me. I was not expecting to fail that many. I went through and I added all those activities because I said I was a bit shocked to discover how many of you do not know you can modify a live website live. Activities were added. The second year, I don't know if it's because everyone saw the numbers from the first year and started paying more attention, or if the activities worked, one of the two. I failed effectively no one, and in my opinion, I did not change the difficulty of the course. This year, I really don't want to fail 20% of you. I have a whole bunch of content up here. You have about the same level of access as last year, who failed maybe one person. But last year I was chasing you and giving you grades for doing your homework, and this year I'm not. So I don't know how this is going to turn out, but these numbers aren't good. I have lecture quizzes. There are quizzes after every single lecture. There is a lot of research on education that basically says spaced repetition is the best way to learn stuff. That means that the best thing for you to honestly do is go watch the lecture. Honestly, I don't post the quiz till like 4 or 5 hours later when I finally get it sorted. But take the quiz that evening, and then right before the midterm, go back through the quizzes. This is the best thing you can do for your own brain. Right, so right now, 61, so about half this class has not taken any quizzes, and only 10 of you have taken all of them. And I did not post the quiz for Friday, so I'm not including Friday in this. The assignment, I can't quite decide how to interpret this, but 86 students submitted Part A, which means that I have about 20-some students that did not do any real part of the assignment. And 33 students submitted Part C. Obviously, I'm not measuring Part B, but since Part B took a lot more effort than either of these two, I'm guessing the numbers are lower. Can I just get a hands up? How many of you have actually tried, at least gotten the VM up, running, and doing something for Part B? Okay, somewhere in the middle between Part A and Part C. All that said, this is a biased group. This group is coming to class. We have 113 students in this room, in this class. I do not see 113 faces here.
This is the first time I'm getting to know about that they're having lecture quizzes.
I I have posted about it on Piazza. I posted an apology last week saying that I am sorry for not getting it up. It's under the content for this, and it was on the first day of slides. This is me though bumping all of you upside the head very loudly. They do exist. One of the things I may be asking one of our TAs to do this week is basically take all the lecture quizzes and try to put them in a singular study quiz where we randomly select from them. Because having you go through all of them in one go is too much, but we can learn to let us basically put quizzes together and then do a random selection out of them. So we may do that. All right, now that I have scared everyone, I'm not going to go through this in too deep, but it's here. It'll be on the Piazza post. This is basically the front page of the exam. It just says that you're answering right after the questions. I have point values in every single thing. You can use pencils and pens, but if you are using pencils, it is up to the marker whether or not they think there is or is not a mark there. There's multiple choice questions, and then I do have some figures provided. Right now I have a small slide deck of the ones I actually provided, and I'm going to be, either me or a TA is going to be going through and adding some extra ones that we might potentially have, and then we will be pushing that out. I do not like, broadly speaking, memorization. I would much rather see you memorize how to use something than memorizing explicit facts or figures, with some exceptions. The definitions, for example, on the first day, you can't define security and privacy. We have a problem already. So I will push out a set of things that I think you don't need to memorize. All right. Any questions on the midterm?
When would you be releasing the answers to assignment 1?
I will talk to the assignment 1 TA and get that pushed out shortly. We have the answers already. I require them to be written before we push out the assignment.
Is there going to be past year exams, or is it?
There are right now. So I have no past midterms because midterms were done differently in prior years. But there are 4 final exams right now on the website that you can pull up from prior years.
So for the assignment, I know like the first 3 questions for everyone, and the later really is for Brad, but you use just like kind of references as well. So you said 30% of
For this exam, partially because I haven't figured out how to do it with the freaking office, everyone's taking the same exam. This may not be the case for the final. I'm working out how to add grad-only questions on the final, but that will not be happening for this exam.
So at the beginning you mentioned like 30% of your like question will be kind of subject to your assignments.
Yes.
So in this
Oh,
case,
no, I
you-
excluded those questions for the midterm.
Oh, but that's not applied for midterm.
So, okay, half the class is what I'm talking about. The assignment had a section on there for master's students only. Content in that section is examinable on the final only for master's students. I have not figured out the logistics of doing that for the midterm, so that section will not be on the midterm for master's students. I will not be examining definitely I will not be examining any undergraduates on anything marked master's student only. I don't know if that is clear or more confusing.
Quite clear.
Okay.
I mean, if it's clear to me, then it should be clear to everyone.
Okay, I'm gonna do 10 seconds to remind you about man in the middle. If you have taken a networking class, which we have 2 prereqs for this class, I believe networking is one of them. We have prereqs mostly to reduce the load of learning about stuff. So if you took the networking prereqs, they should be fairly easy. If you have not, then pay attention. This is a crash course in networking. I will be talking a little bit about security, but 90% of what I'm talking about is just a crash course in networking. I'm also reminding you why we're bothering with any of this, which is that man-in-the-middle attacks happen. And I'm just going to quickly step through three kind of granularities of a network, and then I'm going to roll all the way back. So this is how most people think about the internet. I have a laptop, it connects to this cloud thingy, and then somehow it gets to a server. In fact, most people don't even get this detailed in their understanding. It's actually a bit different, and we'll see this, I will step through how this works later, because you actually send a message, and that message kind of goes through cloud traffic. Sorry, I forgot to take the animation off this. and messages go back and forth. Actually, it gets a whole lot more complicated than that. So this is a little picture here of a network. They're connected by the internet, but each of those endpoints is usually not singular laptop. And this can get quite complicated. So we're going to kind of step through some of this. You'll have seen all three of those diagrams several times. But right now what we're going to do is back all the way up. And man, I am, having worked in usability for a long time and dealing with master students for a long time, I have stopped assuming. So we are going way back. So messages used to be sent via telegraph. We already talked about this before, right? You have a little wire, and you go beep, 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 beep. Most of you are in electrical computer engineering. You should be quite aware that you have signals that are high, signals that are low. Things like Morse code are based on this concept, right? You do a high signal for a certain distance, and then a low signal, and then maybe a high signal for a short distance. Oh wow, I've invented binary. And so this is how we used to send messages. But the problem is that when it was just like one telegraph office in one city, another telegraph office in one city, now I have a dedicated line between the two, and I can send what? One message at a time. Oh man, that's annoying. Ooh, sorry. I'm getting an incoming call. Sometimes those are scammers. Ah, it's a scammer. Hello? Right, it's not a scam. Charles previously on this phone. Anyway, I think I've never successfully gotten a scammer off or something that starts with hello, may I speak to Charles? Let's just put it that way. All right. So how do I do this? Do I just run a lot of lines? So now do I need to run a different copper cable? Like if I have two copper cables between two cities, now can I like have two telegraph operators? That bandwidth seems pretty awful. So how do I do this with a signal high-low? Because I do need that wire. Well, what if I try something called multiplex? So it might be easiest to think of this as colors if you're not ECE. What if I sent some of this in red and some of this in the blue spectrum, right? You can pick different spectrums, and I go and I use a computer system to go and send my beeps across one spectrum and a different spectrum and a different spectrum, right? So now I can use maybe 5 or 6 people on the same cable. Cable's expensive to run, especially when we're in Canada or the United States, which are very wide countries. This is great. Now we can send more than one signal, but it's still quite expensive to directly connect 2 computers this way. Like if I have a computer there, a computer there, I have to run a wire all the way to the computer. This is not, what if I want to go talk to, I don't know, San Diego, and no one wants to connect to San Diego, so we have to go through a different route. So now I have 2 operators involved. This is kind of problematic. This takes us all the way up to 1984. And we thought, I know, we'll do ring of computers. They've shown this like it's a small office, but in theory you could also do this across a large space. It's just wires. So now what you do is you have a singular wire, you're kind of stuck with your singular wire, and every computer is basically passing from one to the next a small binary token. And if you see the token go by and you want to send, you take the token off the wire, which is to say you don't forward it, and you drop your message on the wire instead. Now your message goes round to, and the computer who wants it picks it back up. And then you drop the token back on the wire, the token goes around, and the computer that wants to send next picks it up. Because we want to make sure that 2 computers are not talking on the same wire at the same time. You can imagine scaling this up for multiplexing or something. But the main point here is that you don't want 2 groups transmitting at the same time, we'll have a problem. But this raises a couple minor concerns. When we had just 2 ends to the wire, where the message was supposed to go is kind of obvious. It's going to the other end of the wire. Once I go and I bring this in, now there's more than 1 end of the wire. There's 4 in this picture. So now we have to add in some extra bits. So we need to start actually specifying what the messages sent look like. And so here what you're seeing is 8 bits that just say, oh, here start the message. There's things in here like destination address, source address, and something that kind of ends the message. So now when you're sending a message, if it's not a dedicated line between two groups, and we're not a telegraph where the moment it stops, that's ending, now we need to be able to say, okay, where is this message going? Which computer should pick it up off the wire? And we need to be able to say, like, here start my message, here end my message, such that it goes through and then I can go and put the token back. This raises the concept of something called a datagram. You've probably never heard of a datagram. This is also broadly speaking a packet, but we're going to go with datagram for a moment. A datagram is a self-contained independent entity of data carrying sufficient information to be routed from the source to the destination computer without reliance on earlier exchanges between the source and destination computer and the transporting network. A datagram is something that allows somebody to cold call another computer, to call without any warning and have it just automatically get to the other computer without the other computer need, I don't know, physically switch things. And without reliance on the transporting network. So we're not making detailed assumptions about the transporting network. We have some assumptions, but we expect buildings to use it. I have forklifts down here because if you look at the global shipping industry, the global shipping industry was revolutionized by the concept of a pallet. I know the rest of us are thinking, oh, this is so unexciting. But there's this little piece of wood sitting down here that the forklifts are grabbing. That is called a pallet. Whoever invented a pallet revolutionized global shipping because now what do they all do? Everything is built to the size of a pallet. And all transportation lifting stuff is all built to pick up this one specific thing. This tiny piece of wood at the bottom is actually this interface that allows you to load anything from a washing machine to a bicycle. All the same way and all the same shape. If you walk into a place like Costco and you look up, you're like, oh wow, someone has built this like a grid. Packets or datagrams do the same thing for networking. It creates a standardized shape by which we send data. Now, just like those forklifts, I can use the same forklift on a washing machine, a ton of bricks, a ton of gold bars, a ton of bicycles. It does not matter as long as they fit on the pallet. They have a certain level of balance on that pallet. And all the pallets are built to have the same shape of forklift, pick them up or down. We are doing the same thing, we're just doing it digitally. Alright, so token rings is how we briefly tried to solve this a long time ago. But let's start talking about how we do this more modern. And I'm going to kind of step us through this slowly. So one solution we could use here is each computer breaks their messages into datagrams of a max size. So similar to that palette, we want a specific shape to our datagram and we want a certain maximum size. We don't want people just taking the entire wire at all times. Kind of makes sense why you would. Then those datagrams are put across the wire. Now we can share the transmission line. And we can decide, though we still have this problem of deciding who to send and how to handle things like collisions. So our two big problems in this are collisions and congestion. The idea, let's see if it's an animation. No, it's not an animation. Okay. The idea here is that this computer sends it down to a thing I haven't discussed yet. This computer router basically sends these packets. Computer sends those packets to a local router, and then the local router puts them on the line. Now they may not go in the same order. Here we have blue, green, yellow, yellow, green. Green is probably the same message. It's just been broken into two diagrams. This is not that different from say sending a pallet full of two pallets full of books. Maybe one book pallet goes on one truck, one book pallet goes on the other truck, but as long as both trucks make it there, we don't really care. Same concept. But we have a couple problems here. One of them is collisions. So what happens if two of these hit each other? And one of them is congestion. What happens if this wire is too full? So what if this input here sends too much stuff here such that we just can't fit it? To handle these issues, we use something called protocols. Protocols are kind of like algorithms, but they're not if you talk to the algorithms people. A protocol is basically a set of rules that have been come up with rolled out across the entire internet. So the protocol is a language or set of conventions on how two computers are going to interact. So that token ring I talked a moment ago, where things are going around, that is a protocol. It has a set of rules. It says you will not transmit unless you're holding the transmission token. You will send things, but only of a certain length. And all the packets you release on this network must have this structure. And that's what you're looking at here. And protocols often handle things like when to send, what an end of a transmission looks like, and what the packet structure should look like. So here's an example of a packet structure. It says things like, 8 bits for this, 8 bits for that, 8 bits for that, and then there's a whole message in here, usually. The message you can tell because it has, see, this was like up to 4,500 sets of 8 bits. Packet, which we were calling a datagram half a moment ago, is the smallest individually addressable data unit you're going to transport. Packet is a very simple concept. As I talked about, those pallets, those wooden ones, if you ever stared at one, they're not very complicated. It has a destination address, a source address, and a message, bluntly speaking. That is what a packet has. They're usually created in layers. So I say it has a source, usually has a source, a destination, and a message. Usually has other structure around those. But you might start something here where you have maybe a message, and this is a header that has source and destination. And then that falls down, and then we add a different source and destination to the front on top of that. You can kind of think of it as having an envelope that is destined to, let's say, the United States, and it gets put in a box of all envelopes headed to the United States, just marked post office in U.S. That whole box goes to the U.S., we open it, and then we send out the local letters. You get this. So you get these and this happens in normal networking, where you're just kind of encapsulating things and treating each layer, kind of treating the message as also having content inside. All right. So all of this is coming down to this basic concept. How do computers or routers know where to send datagrams? And how does a computer know when to pick up a packet? So I keep talking about like picking it up or dropping it or putting it on the wire. Computers usually work by passing things along. So you get something that's not for you, and you just put it back on the wire and send it on to the next thing. I hope it'll be there. You don't always just hope. I will get back to that topic. But in the token ring example, here we are. What's happening is every single computer is picking up. Is this for me? Nope. Put it back on the wire, retransmit. And the same thing is going on here, right? These messages are coming in to this point, it's being sent across the wire, and again, we have to know where to send them out the other. And this is packet addressing. I think I have more details. And my computer has broke. Okay. It just went really fast through a lot of stuff. So we have these, but we haven't really talked about how they're generated. Like, what's an address anyway? You think of an address normally, you think, oh, that thing written on my house that doesn't move. Usually when we talk about physical addresses, we mean things that don't move. But your laptops move around a lot. So do your cell phones. So how are we doing addressing here? One way of doing it is something called a MAC address. This is a medium access control address. And it's mostly, we're going to pretend for the moment it's assigned at the time of manufacture. It is most of the time. And this can be used to identify six groups of 2 hexadecimal digits, and it's used to identify unique devices on a local network. All of your computers probably do have a MAC address. I think this thing may even have a MAC address. Just about anything that can be on the network usually has a MAC address. So that includes your phone. Yes, it is possible to spoof MAC addresses. No, most people don't.
Actually, that's by default.
So yeah, some phones do MAC address spoofing by default to do privacy. Because your device's MAC address doesn't change, it's baked in from the day of manufacturer, it makes it really nice for tracking. So things like phones will sometimes try to hide their true MAC address from random apps. And you will sometimes get like Wi-Fi network routers will try to use a MAC address to go and track people across routers and do things like that. So sometimes phones will spoof these. Now you can use these to identify. So if I now have this small token ring example here, everything has a unique address. So now it's really easy to go and write that address onto this packet. I go, this is for computer 4796223. And that goes around. And when it hits you, you know what your own MAC address is, you pick it up and you look at, oh, this is mine, and you don't forward it along. Alright. That's basic. That works because, again, every single device is pushed out about this, but it shouldn't take very much imagination to go, well, our networks don't look like this. They are nowhere near this small, and it's not the case that you want every single computer to see every single message. Back when I was an undergrad, we used hubs and not routers. A hub broadcasts everything to every computer. A router will specifically send data to where it's supposed to be based on that. But in order to send data to where it's supposed to be, I have to know all the addresses across my different interfaces. So to handle this, we started creating something called IP addresses. So this is an IPv4 address. I will briefly mention IPv6 occasionally in this class, but I'm pretty much staying with IPv4. We are getting better at rolling IPv6 out, but it is harder to explain to people, and unfortunately IPv4 seems to be here to stay for at least the next several years. So we're staying here. You'll see me occasionally mention IPv6. They've been telling me that IPv6 is going to roll out ever since I was an undergrad. Anyway, it's getting better. IPv4 address looks like this. It's what we call dotted decimal notation. Technically, it's 32 bits, but it's got 4 numbers, and it's written in a hierarchical fashion. You've probably seen these before. They're usually, if you look on your network card, you're trying to connect with another computer, you'll suddenly need to know this. Every computer on a network has an IP address, either IPv4 or IPv6, which is unique from the other computers. This is very important. If you ever actually have 2 computers with the same MAC address or 2 computers with the same IP address, it can really muck up networks. Each interface on a computer gets its own IP address. If you have, say, 2 network cards, you have 2 MAC addresses and you have 2 IP addresses. If you are doing a mobile hotspot, you now have your IP address you're using to connect up to maybe a cell phone, and you have a different one that you're using to connect to whatever the device is that you're sharing that with. Every interface has its own IP address, and so yes, your computer can and often does have more than one of these. Also, if you use wired networks, so your Wi-Fi address will be different from your wired. Here's some examples of this. So what you'll see here is 2 computers. I'll get into what 192 is in a moment, but you see like these 2 computers here have different IP addresses. There, you only need a different IP address on one network. So I thought this example was actually about to do. Is it perfectly fine if this computer and that computer have the same IP address? Because they are on different local networks. There are 4, maybe arguably 5 networks on this screen. One of them is this home network here, so everything here needs to be unique. One of them is this corporate network, and one of them is this tiny network. Inside each of these boxes, you need unique IP addresses, and then the 4th one is called the internet. And again, across the internet, all addresses need to be unique. This is why we are slowly shifting to IPv6. It has a larger range. We have run out of IPv4 addresses to use on the internet, but they must all have unique ones. And this is the rule we cannot break, and therefore we have to start. And you'll see that each of these routers on the edges, they have two from two different address ranges. So like this one will have this one, this that one. Two of them because it's bridging. It's basically taking traffic here with this IP address and then bridging it over onto the internet visible one and sending it out. You can totally look this up on your own machine. You can even just type, what is my IP address? Actually, that's a good point. I've typed this question locally. I think for both of these, I was sitting inside of a university. Yes, I was most definitely sitting inside of a university at the time. If I query out onto the internet and say, what is my IP address to the website? Am I going to get, actually, this is a good question. I'm going to use this as Think Fair Share because I'm a little concerned that we don't have one in here and we're about 40 minutes in. Sorry, I spent a bunch of time on the midterm and I did not vet these slides as detailed as I normally do. These are the easy slides to present. So I'm going to do a Think Fair Share on this. I'm going to ask this question. Imagine you have this home PC here, 192.168.4.2. It's connected to this router, 192.168.4.1, which is also known as 131.255. You go, I want to know my IP address is, but I'm not a software engineer. The internet would know. And so I type in, I go, what is my IP address? Which causes a web request to the website. What IP address is the website going to tell me? All right, no one answer. 1 minute. Think about that. And you can try this yourself. You can. I did not give an example here for Macs, but I think Mac uses ifconfig as well, right?
Should.
You can pull up your local. You can ask a website, go, who am I? And it will helpfully tell you. The other thing you'll notice is your IP address changes. So if you do that here and then you go home, you have a different IP address. But your MAC address does not change. Your MAC address stays stable because it was created inside this machine. Again, we kind of use this throughout networking. So what happens if that router up there, which is the current thing that is giving everybody in this room an IP address, and then you close your machine and you walk across campus to another spot. Now, I actually don't fully know the answer because it depends on how they set things up here. How does it actually know you're the same person? I mean, one way is we've got some login stuff, but usually we don't want to expose the login stuff to the network routers. These things are very vulnerable. You can take a screwdriver stack, get all the data on it. One way is by tracking your MAC address. So you go and you try to connect again, and it goes, oh, this MAC address. Oh, that MAC address was assigned this IP address. I will just give it the same one. My guess is that if you cross campus, you will keep the same IP address, at least within the singular day. But if you close, you go away for a week, come back, you'll probably get a new one. But not completely a new one. Usually the first few numbers will be the same. I don't remember, are we starting all ours with 192.168? Doesn't matter. If you look up your IP address now, the one in your local machine, the first two blocks, possibly the first three, will be the same almost every single time you try to get an IP address on campus. But when you go home, they may be radically different. What's going on here? This is me highlighting this. Oh, we use running trace routes. IP addresses are organized into ranges. So our goal is to do global addressing, right? Our goal is to be able to go and say, oh, I want to speak to this computer in China. Just sort it out. And if we have to track every single MAC address across the entire planet and what IP address is currently associated with, we have a problem and we cannot do routing. So instead what we do is we have built IPv4 anyway as a nice hierarchical structure. It's got 4 numbers. If you've ever looked at phone numbers, specifically landlines, they do the same thing. The first set Well, the very first number tells you what country you're likely in, and then the zone of the country is the next three, and then the 3 and the 4 after that. It varies a bit by country, but those are usually done again physically zoned back when we had landlines. It's still signed out that way when you first try to get your phone. This is a screenshot off of University of Edinburgh, who actually exposed this information. I can't find it for Waterloo, but you're seeing here is an IP ranges. So 129.1215.31.248, all the way up to 255. Those are all this building. They're basically saying these are the IP address ranges by building in Edinburgh. So if you're in this particular building, you will be given an address range here. If you're in a different building, you'll be given a different address range. I think this is for the wired building. This is so they can do routing inside. Now if they actually get a request in and they're like, oh, this destination is in this range, they know what router to send it to. And you can see that. So I forget which. Apparently, I was in the informatics forum at the time, which makes sense for my offices. So when I ran this, it's like, that's your IP address because that's where you are. We call these reserved ranges. So we have 3 levels of ranges, or 4 levels of ranges in IPv4, or three levels. You have. Sorry. I think I'm being talking quick for this discussion. I am. Alright, so general addresses, we have a large set of general addresses, and I'll come back to those. But we actually have several special ranges. You will see 192.168 a lot across many networks, and you're like, why is it every home network uses 192.168? What's going on there? And the answer is that we have these 2 private ranges that are used a lot. 192.168 seems to be the default all the time, and then the 10 range. And those zeros afterwards just mean anything from 0 to 255. So this range here, these ones are not allowed to be used on the open internet. If you ever see an address coming in across the open internet from those ranges, there has been an error. These are meant entirely for home use, and you can use them for whatever you feel like. They're open for use. Same is true for the B. Loopback, though, I don't see this one very often. Loopback is the 127.0.0.0 range. That means your home computer. So if you ever type 127.anything, it will attempt to access it off of your local machine and not access it otherwise. So if you've ever built web pages and you can kind of do, sometimes you can spin up a local server on your machine when you're debugging that web page, or I suspect also actually our password game does the same thing. Suspiciously, the IP address is in the 127 range. It's a special address. These are almost all designed for local maintenance and testing, and they're also set as, honestly, you could use any IP address you want on your home network. You can do whatever you want. It's your own domain. This is error prevention. If you use these and any of those IP addresses get out, there's no errors, because what happens is the next router to see one goes, no, and just drops it on them.
You can't do 2 layers of the same range.
2 layers of the same range.
I tried doing it. I tried connecting a router behind another router that both uses the 192.168 range, and that.
Okay, so that's not in the protocols to my knowledge, but that is probably a decision they have made. We are always talking a combination of theory, protocol, and implementation, and the 3 are supposed to line up, but not always. Again, this is me just showing a picture of me sitting behind one of these in that range. Also, you'll notice the addresses I have picked here are not accidental. The ones inside the range here are definitely kind of within the 192.168, and the ones out here I think I've just picked randomly, but they're not within one of the protected ranges. So you should never see a protected range one out here, and you will often see them inside networks. I don't remember, I keep taking natting in and out of this class, so I don't remember where it is sitting for this round, but this jump here, this movement from inside to outside is something we call natting. You can look it up, I may be covering it briefly later.
So I'm just curious, how would you define like a network?
A network is just defined as a set of computers. Usually a network in this context is something that's all within a certain network, a certain range of IP addresses. And you need some sort of global, or you need, across the entire network, you need some sort of strategy to hand out IP addresses where you don't have collisions.
So I'm just curious, like, in real world, how would you categorize and how would you categorize the set of devices as a network? Like, do you have that?
Oh, if they're just not connected. I mean, okay, so there's creating a network and there's managing a network, and they are related. So I can just run a cable between two computers and I now have a network. I can connect a whole bunch of computers to the same Wi-Fi router, but not connect it to the internet, and I still have a network. Usually we talk about the boundaries of a network in terms of its management, because it's vitally important we not have IP address collisions within a network. Usually a singular network is managed by a singular person or entity. So this university, for example, is a singular network. Broadly speaking, we have a bunch of sub-networks that kind of broken off and done things, but as a singular entity, and that entity is in charge of deciding how those IP addresses are put out and ensuring that collisions do not occur. Usually, whenever each entity will self-declare itself in terms of a network space, so they'll say, okay, I am this network space, I manage things in this network space. Oh, I did have a question. Huh, forgot about that. All right, we're late enough. I will turn this into a point instead of a think, pair, share. Let me just check how many slides I have left. Think about that on the screen while I check that. Oh goodness, yeah, we still have to get through all of OSI network model. We're not doing that as a think, pair, share. Let me make a point instead. You remember reference monitors? We learned about them back in authentication. Sorry, we learned about them back in access control. So in order to have an access control system that's functional, what must every single request do?
Tell you who they are.
That's authentication. It must go through the reference monitor. If it is possible to access a file or resource without going through the without going through the reference monitor, you no longer have access control because you have lost control. Every single request must go through this. A common problem I have yearly is that all of you sit there and stare at me, but I type the web address into my browser and I hit enter. How could I possibly end up at any other page? You're basically saying when you ask me that question that you think this is going through a reference monitor. The reference monitor. Who makes certain that a packet goes where it's supposed to go? In a way that, at the level we were talking about with access control. The short answer is nobody. A network is built of a whole bunch of parts from whole different groups that may not even trust each other, and we don't trust them. And it's intended to be cobbled together from many different groups. There is no reference monitor. These groups here are called routers. They are not called access control enforcers. Their goal is to route things where it needs to go, like a mail sorter, but they are not security. Their goal is to do this as best as possible. There's nothing stopping them from not doing it. If they suddenly decide to route all this traffic that way, it goes that way. There is no global internet police. And this is not an operating system, so there is no singular entity that's controlling all access. Your network traffic goes out there. Best hope it gets to where it's going. come back to that because I swear, even after saying that, I will get this question again. In some ways, I'm happy. We have done such a good job of security. You all believe that it just works by magic. And the other side of me is unhappy because you're engineers, and dear goodness, the magic needs to go away now. All right, we're gonna dive into something called the OSI network model. We are still on networking. We are not on security yet. The OSI network model is 100% theory. There is no such thing as any system built this way. That said, every system is broadly speaking built this way. It is a theoretical model of how we do things. This is meant to help you understand how things are processed in networking. So the idea here is that you have these layers. You have the application layer, presentation, session, transport, network, data link, and physical. The idea is that a packet or an application, let's pick up Firefox for a moment. Firefox creates some data, and we need to somehow convert this web page that Firefox has all the way down into beep, 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 ones and zeros going across the network. That's one heck of a conversion. And in modern software engineering, we take a modular approach. What do? We don't figure out how to do this. We call a library. And that library calls another library. And that's how this is done. I'm gonna go through this much. So, you can also think of this in terms of debugging. Let's say I can't, my network isn't working somehow, right? If I browser, can your browser open another website? So if you try to access this website, but you need to access another website, then your problem is sitting all the way up here at application. Can you ping the gateway or the DNS server? So can you ping your router? At which point your problem is probably sitting here in transport. Do you even have an IP address? Because IP addresses start being added about this point. Is the light on the modem on, or is the light on the network connection on? Maybe you don't even have a physical thing that's creating it. All the way down to, is the network cable plugged in? The bottom is very physical, very physical. We mean like cables. Is there something blocking the signal? The top is very application looking. It's things like, do you have a viewer for this? Because if I get in a bunch of bits and bytes, and I just put the words JPG at the end, this does not make it renderable. You can only render that if you actually have something capable of rendering bits and bytes called JPG. All the way up to the application itself. What kind of things is it even trying to do? And this is how we are trying to get information across the network. But also keep in mind those upper layers. Here's a simple example. We've got a Firefox user and we've got an Apache web server. So the Apache web server on the left. The Apache web server here on the left. It has created this website. So you've got a whole bunch of pictures here of HTML. Admittedly, the application may have had something else, but HTML is pretty much what's being sent down to the presentation layer. Here's a whole bunch of text. Send it. Great. The application, then that passes down to the session layer. At this point, we try to go and actually set up an internet connection between the two. And at this level, the library is basically calling, oh, this is a session, a connection, these nice big words. And you drop the whole website into the connection. Then we start moving down to end-to-end transport. All right, now we have to actually talk to that other computer. We have to set up something so that we can send all of this data. We might start talking about the network itself. Okay, what's my IP address? Do I have an IP address? Who am I going to send this to? Because I can't just drop something on the network, right? You don't drop things on the network. Your computers are all talking to that network router up there. So where's my router? And which router does it need to be sent to? If I have more than one interface on my thing, if I have two network cards, what network card does it need to? And so you start figuring out these logical addressing. You make a data link layer. So now I have to actually make a connection between two machines, not an infinite number, two. This machine and the next machine is going to. What is the next machine is going to? Again, in this room is that router. But maybe on a wired connection, there may be a couple different ones. And then finally, where's the wire? Or where's the media signal? So I now have to actually go through and convert everything into a wireless signal and send it. And once it goes across this line, it comes across a whole bunch of ones and zeros, and we have to go back up. So now we have to put all the packets back together again. We have to reassemble them. We have to convert them back into a JPEG. We have to make sure that JPEG goes to something that can render a JPEG. We have to make sure that rendered JPEG makes it all the way back up to the application in order to produce a website. So messages start up at that top layer. In this example, I'm not actually breaking messages up. Let's just assume we have something small enough that can fit in one packet. In this, we also, part of the session there is actually breaking up something about the right size. So for that top kind of purple section, we're pretty much not adding anything. We're changing the content of the message. So we might be converting something into a JPEG. Maybe we need to gzip it before we send it. There's a lot of things. Maybe the other computer has informed us that it only speaks French, and as a side effect, we maybe have to do a conversion into French before we send this content. So all of this is kind of more up at the software stuff that the user uses. Then we hit the transport layer, and then as we move through network, data link, and physical, we just start adding headers. Because every single one of them works at different levels. The network layer is caring a lot about IP addresses. The data link layer is caring a lot about MAC addresses. And physical layer, again, where's the wire? Which wire am I sending across? And each of those require headers and often sometimes tails. Routers should be able to route traffic without managing content. So I'm going to go back a couple slides. This is the source computer and the end computer. But as I showed you at the beginning of the lecture, it goes through a lot of computers. And some of these things are things that each computer needs to do differently. So if I'm routing with MAC addresses, if I'm using MAC addresses in my head and tail, that only is good for two computers, one hop. So what's happening is that the majority of the time when something is passing across a router, it's having to parse up the OSI network model a small distance, rewrite, and pass it back down again. So it's not always the case that I parse all the way back up, or all the way down and then all the way back up. It's much more normal that I'll parse all the way back down, and then the intervening things may go and try and parse a small distance up in order to figure out, okay, where's this thing actually headed? What's its IP address? If it's that IP address, that means that the next hop needs to be this MAC address. And then it's continuously rewriting MAC addresses the entire route across the internet. This is a screenshot of a program called Wireshark. We are working on creating a new coursework that will not come out until after the midterm. In that we are trying to get Wireshark up and running for you guys. I will not promise until I have seen it, but you can download and play with this yourself if you want to. Oh wait, am I running? Wireshark is a very common method to go and capture network packets. And you can see the layers sitting here. So you have the physical layer. It's got words like frame in here, interface ID. I think so. I don't know if it even has the MAC address. But it has things like how big this packet is. Again, this is 2 points, wire to wire, across one wire, packet being sent. And we need to know where the start of the packet is, and we need to know the end of the packet. We have the data. And then we jump forward, we get to things like IP addresses. So now it explicitly states this is IPv version 4. It's got the protocol we're using, in this case TCP. It has the source and destination IP addresses. And then if we get further on, we'll get more content about what's actually in this message. Okay, so when I say information is added, I actually mean what's on the screen. It's being added as it goes down the network layers. This is me visiting /dot.org. 6 packets were actually being sent in this case. I think it's colored though, if I remember correctly. There's kind of like a bit of a red and a bit of a blue color. Those are different packets, and then this has been reassembled by Wireshark for me. So 6 packets were sent from my computer, 50 packets were sent by the server. This is me visiting my own website. There's no HTTPS. And yet this content sure looks garbage. That does not look like a web page. My computer has helpfully zipped it for you. The server said, oh, could you please, I'd rather send this in a truncated format. And the other machine said, sure, no problem, let's use less network space, and truncate it for me. I give you this, effectively gzipped it for me, they compressed it. I put this up here mostly because one, a chunk of you will tell me, oh, this is encrypted, it looks garbled. It is not encrypted, it's gzipped, and that happens a lot. And two, there's kind of those purple sections at the top of the IOSI network stack, and you sit there and think to yourself, oh, those are just applications. Those are just like Firefox. They're not part of network routing. But actually, those initial top ones are doing reformatting of the message. And one of the reformatting stuff they sometimes do is compression. And that compression is, we can argue if it's part of networking or not, but it's part of preparing a message to go across the network and use the least amount of space necessary. All right, I'm gonna try to get to TCP in the time frame that we have available. All right, up to now I have been in fuzzy land. We are, broadly speaking, been talking about things in theory. TCP is an actual protocol. How many people have heard of it before? Okay, shockingly not the whole class, but close. That's good. Do you know why we have it?
To control transport or transmission.
Yeah, no. So we talked about how the network can just lose things. There's nothing stopping it from just losing stuff. Networks are not reliable. Some backhoe driver thinks to themselves, I don't actually need to call. There's probably no wires here. And then takes a big backhoe and just like cuts an entire network line. Unfortunately, wars happen. Undersea cables get cut. All sorts of stuff happens. And that's just talking about occurrences that are non-malicious. Your networks are a lot less reliable than you think they are. They break a lot. And packets get lost. How do we make sure all the packets get there? This is the point of TCP. TCP is trying to create the illusion that there is a singular wire between your machine and that destination, and all the stuff is being sent along that singular wire. And that a programmer should not need to worry about packets being lost. They should not worry about where the packets were sent. They should not worry about whether they're going over Wi-Fi or anything else. They should just think about this as a socket or a connection that things are being sent across. Things that we worry about, not reliable. Packets arriving out of order. Do you really want one part of your website showing up above where it's supposed to be? Like, should developers be worrying about that? Well, no. And the other one is congestion. If you send too many packets at a router, its buffer is limited, and it will sometimes just drop them on the floor. And when that happens, what now? And so the idea is TCP handles all of these sorts of things. TCP is trying to create the illusion of this. So this is a total fabrication. But the way a developer programs is if this was true. Developer programs is if it comes down, it hits their session connection, they drop all their data into the session, and it just pops out the other side. Magic. Networking's primary goal is to make this happen and make it invisible. And that's why this one basically ends right above here. This is where TCP is living in transport. So TCP creates a pipe where it makes sure that data is transferred through with high reliability and not lost. TCP is good for reliability and less good for speed. There are other things that do speed much better. And TCP breaks messages into smaller messages that fit well in packets. So you'll send all the data down to the TCP. TCP will then start chopping it up, and it does not care if this is the nose of the dog in that image or what. It's just like, this is bits and bytes. I will take this chunk. Fits them into packets, and each packet is assigned tracking information. In this case, sequencing numbers. It is not 1, 2, 3, 4, but we're gonna go 1, 2, 3, 4 for the moment. The idea is this is the first one, the second one, the third one, this is the fourth one. And they are ordered. And you can kind of see that here. So the idea here is we have the transport layer, which is what we're talking about here. Message, we have a TCP header here, and then below this we have the other messages. If you pull this up on Wireshark, you will see, well, this is, okay, I'm not gonna get into this, but this is what the header actually looks like according to the protocol. TCP is based on the 3-part handshake. It has to do this. So up till now, I've been talking about network connection systems. They just like, we drop a packet, it goes there, and that's the end of the world. But now we have more than one packet. We need to not lose them. But how do I know if I've lost something? So imagine dropping a bunch of letters into a post office box. How do you know that the other group got it? You have to ask them, don't you? There's no other way. And so TCP creates a connection where we're coming back and forth with each other to answer the simple question, this is what I've sent, this is what I've got. But keep in mind, those are also packets. So if I am losing packets, there's a good chance I'm also losing some of those packets. So this is unreliable. So we start by setting up a connection going back and forth and trying to make sure we can have at least one exchange before we drop anything on this wire. And we call that the 3-part handshake. So the idea here is we do SYN, ACK-SYN, and then ACK. And so the idea here is Alice sends to Bob a SYN packet with a number. Bob says to Alice that number plus 1 back, and its own number Y. And then Alice sends to Bob acknowledgement that they got Y plus 1. This creates 2 numbers, X and Y. These are our 2 sequence numbers. For security reasons, these are picked at random. They're used sequentially from that point forward, but they are picked at random. And because they are random, it is necessary for both sides to acknowledge that they got it. Once we're finished with this, it is now possible for Bob to send to Alice using, I think they use their Y, if I remember correctly. Let's see, so Bob, yeah, so Bob, every time Bob sends a packet, they sequence starting with Y. So all of Bob's stuff will have a sequence ordering, and all of Alice's stuff will have a sequence ordering with X. Alright, are we still with him? As I said, if you've taken networking before, it's easy. This is an example of a SYN packet screenshotted off of Wireshark. You have a set of packets here. Yeah, so you can see them up at the top. The SYN, ACK, ACK. This is the ACK one. It's got things like source and destination port. I think it's got the IP address in there somewhere. Oh, yeah. That was the SYN, there's the ACK, and this is the final ACK back. Alright, we're setting up a connection. Now that we have a connection, we can send the first message. And so here again, you're seeing this message being sent. And it's using TCP. This one's also using encryption, which is the transport layer TLS, transport layer security network. But you can see it going in, having to get source port, destination port, sequence numbers. Wireshark is helpfully creating what they call a relative sequence number, which means this is Y plus N, and it's showing the N. Alright, great. Now I send messages. How do I know that the other side got them? Right, so now I've got my handshake, we've got sequence numbers. Yay. Okay, so now every message I sent has a sequence number. And I will keep sending messages. So usually, okay, now we're getting the stuff that the networking researchers actually work on, and you can get to a lot of complexity here if you care. But the main point is that they send a set of packets, a whole bunch of them usually, at the server. And then the server will go and tell it periodically back, oh, I've gotten every packet between 5 and 27. And they'll send those back via ACK messages. This is an ACK message. So what it's saying here is, oh look, I'm at stream. Okay, it's saying, okay, I've gotten, sequence number, this is the next sequence number. Oh, there it is, okay, acknowledgement. So here's its acknowledgement number. It's basically saying, I acknowledge getting the packets up to this point. And I'm now being a little nervous because I haven't stared at this in a year, and so any of the network engineers telling me to parse this differently, but the content contains, what non-packet number is got. If it gets something back that basically says, oh, I haven't gotten these, or I'm still waiting on this packet, it resends. So the most common method for a system to handle is it goes, oh, if something doesn't get through, I'll just send it again. We haven't really talked about how the internal networking system works, where things kind of get moved around inside of the internet, but things are designed such that if you start losing a lot of packets in a particular area of the network, it will stop routing things through that area. So what will usually happen is if TCP is failing, if you're not getting the connection through, it'll just wait a few moments and then it'll send it again. And just assume it got dropped due to congestion or dropped due to something else. If this fails too much, you'll start getting errors. But it will, if you get lost packets a lot. And then it does this connection by coordinating the sequence numbers, both in terms of sending, making sure everything gets through, but also in terms of, I got a pile of packets in here, and now I take all these sequence numbers, and I rearrange my packets based on that. I put them back together into the message, and I send them up the OSI network layer, the next layer, parse. Yeah, so one of the biggest causes actually of loss is just simply too much traffic being sent to a single point. So if you have an input queue, you have an output queue, you've got all these packets coming in, you buffer them, then the router goes through and every single packet's gotta go, okay, where's this one going, where's this one going? That takes a little bit of time, and then it drops in an output queue to go out onto the network. If that input queue gets too big, it just starts dropping packets. So if a packet comes in that's above its buffer size, it just doesn't do anything with it, it just deletes it and doesn't do a thing. And it assumes that the computer that sent it will just sort this out by sending it again. And this is how it detects an edge. So alright, we're pretty much out of time, but this is an example of what I'm actually talking about. So Alice sequences, it maintains a range of which ones have been sent that they don't know about. And there's a Bob act. What was the last packet that Bob acknowledged getting in sequence? And then was always balanced. And they're always coordinating sequence numbers. They're very chatty. I'm gonna stop here. I will cover ports on Friday. Alright, thank you very much. That's it for today.
Good job, thank you.